Assalamualaikum and have a good day everyone. My name is Nur Fatihah binti Cik Rosni. I am the funniest student in Bachelor of Mechanical Engineering. The title for my undergraduate project is Optimal Generator Design for Low-Speed Wind Turbine. My supervisor is Dr. Kamara Fizam bin Ismail. For my presentation, it will cover 5 chapters. Chapter 1, Introduction. Chapter 2, Literature Review. Chapter 3, Methodology. Chapter 4, Result and Discussion. And lastly, Conclusion. In a wind turbine, we could divide it into 3 systems. Firstly, the primary energy which captures wind from the surrounding. When it comes to the low-speed wind turbine, the wind speed is lower than 7.5 meters per second, and it usually comes in small size and lighter. Secondly, the conversion system. Here comes in the generator. A generator has a relative movement between a coil and magnetic generator. The rotor windings in the generator will feed the electrical signals to the grid transformer. A generator also converts mechanical energy to electrical energy. And the load here is the electricity produced from the generator. The objectives are to design and simulate an optimal generator for low-speed wind turbine and to conduct testing on the fabricated generator by using a test rig. My scopes of study will cover the theoretical findings for the generator designs, such as number of poles, number of winding turns, thickness of winding, and type of permanent magnet used. Secondly, design the generator by using the parameter found from theory and simulate it in the JMAG Designer and Altair Flux. Lastly, ensure the generator compatibility with the wind turbine to produce as close as 1 kilowatt of electricity. Now, let's move on to the second chapter, Literature Review. There are 2 types of wind turbine existed, called horizontal axis wind turbine and vertical axis wind turbine. The difference between these 2 wind turbines is HAWT has plate axis that is parallel to the ground and wind stream, while VAWT axis of rotation is vertical to the ground, while set perpendicularly to the wind stream. These are the type of generator that are widely used in the industry. For this electrical permanent magnet generator, it is often used in a rural area wind power plant. It is a radial flux generator that is suitable for low-speed rotation. The type of permanent magnet used in this generator is neodymium iron boron. For the permanent magnet induction generator, there is no usage of gearbox. The stator has 2 components, which is outer and inner slots to support windings and cooling system. But it emphasizes on the selection of the type of permanent magnet used. Here it can be seen that the type of permanent magnet used is neodymium due to its highest magnetic properties. For this axial flux permanent magnet generator, it can produce up to 1.5 kilowatt of power, and it is a low-speed direct driven generator too. It also made up from non-ferromagnetic core, which is gearless. Moreover, we also can see the magnetic flux here between the stator and rotor, with the peak flux density at 1.041 Tesla, and the EMF output is 0.302 volt. Based on figure 5, the performance factor versus wind speed, it showed that the AFPM generator is much better compared to the other generator in terms of performance factor with the low speed wind. On the third chapter, Methodology, we will see how the project is conducted and the fixed parameters. In this project, the type of permanent magnet used is neodymium. N52 is the highest grade of neodymium in the neodymium family. For the project, the type of permanent magnet used is in the ring shape, as shown in the figure. It has strong and best magnetic force properties, and even though it is small in size, the magnetic force is strong. And it is much more cheaper than the samarium cobalt magnet that come from the rare earth magnet. For the theoretical calculation, these two are the formula used to calculate number of poles and number of winding turns. To calculate number of poles, N equal to 120 times F over P. N is speed in RPM, F is frequency output voltage, and poles is P. The number of poles obtained here is 12. Moving on to the number of turns. To calculate number of turns, EPH equal to 4.44 F5 dph kW. dph is turn per phase, EPH is induced EMF per phase, F is frequency, phi is number of poles, lastly kW is winding factor constant, that is 0.955. The number of winding turns obtained here is 33 turns. The two pictures here show how the test rig is set up. For the test rig, the output is observed by using the oscilloscope. For the type of the permanent magnet that is designed, this is how the rotor and the stator looks like. The stator and the rotor was 3D printed. In the first picture, this is the rotor that is used to hold poles of magnet where the magnet is placed alternately north and south facing upwards. There are 12 poles of magnets. In the second picture, this is the picture of the 3 stator with different winding thickness. From the left, the thickness is 0.5 mm, 0.8 mm, and 1 mm. In this project, there are two types of software that was used: JMAG Designer and Altair Flux. JMAG Designer was used to predict the output of different coil thickness, and Altair Flux was used to observe the distribution of the electromagnetic density flux. Here on Chapter 4, Result and Discussion, we will observe the result from the experiment and simulation. The test rig experimental results show the induced voltage for different coil thickness. From this experiment result graph, these 3 different coil thicknesses show the same trend. When the speed increased, the peak-to-peak voltage output also increased. For 0.5 mm coil thickness at 3000 rpm, the peak-to-peak voltage is 120 mV. For 0.8 mm coil thickness at 3000 rpm, the peak-to-peak voltage is 180 mV. And lastly, for 1 mm coil thickness, the output is 100 mV at 3000 rpm. So here we can say that 0.8 mm coil thickness show the highest output out of all 3. Next is simulation result. This is the simulation result for 0.5 mm coil thickness. So the highest power it can produce is 500 watt, and 24 volt is reachable at 800 rpm, while at the start the torque is at 5 Newton per meter. It decreases slowly when the speed increases. For 0.8 mm coil thickness simulation result, the highest power it can produce is 750 watt, and 24 volt is reachable at 1600 rpm. The torque produced here is 5.5 Newton per meter, and it also decreases when the speed increases. Lastly, the simulation result for 1 mm coil thickness. The peak power it can produce is 850 watt, and at 1600 rpm it can produce 24 volt. Here, the torque is 5.5 Nm and decrease slowly with the increasing speed. From Alter Flux software, the flux density distribution is ranging from 0.941 Tesla to 1.569 Tesla. It can be seen here that the orange-red region between the stator and rotor have the highest flux density at 1.569 Tesla. Next is the cogging torque graph. The cogging torque is produced due to the geometry of generator. Here we can see that the max cogging torque value is 10.39 Nm. One way to reduce the cogging torque is by skewing. Skewing is applying the appropriate angular offset along axial length of the stator or rotor. To discuss this, firstly we will see the experiment result. Basically, a thicker coil wire would carry more current compared to the thinner coil wire as it has more lanes and more surface area. But as we can see in the experiment, the output of the generator is small, which is in millivolt. This might happen due to the small magnetized area. As we can see, the stator of the 1 mm coil wire thickness is way bigger than the 0.5 mm and 0.8 mm coil thickness. So here the exposed area of the 1 mm coil is bigger and the magnet area is insufficient to cover all of the exposed 1 mm coil area. But in the 0.8 mm coil case, the exposed area is fully magnetized and it carries more current, thus it produces a better voltage. Next, based on the simulation result, the most suitable coil thickness to be used is 1 mm. It can be seen from the previous graph that the power output can reach up to 850 watt and it can produce 24 volt of voltage at 1600 rpm. And lastly, the type of winding connection used in this generator is called delta connection. Delta connection means one of the finished coil winding is connected to the starting of the other coil winding of other phase. And the advantage of this delta connection, it is highly reliable. It becomes reliable because of if one of the primary winding fails, the secondary winding is still usable and the voltage output will still be the same as three-phase winding. But it is crucial to ensure that the remaining two-phase is able to carry the load. All in all, I would say the type of generator design that is suitable with the low-speed wind turbine is radial flux permanent magnet generator with 1 mm coil thickness. The material of the permanent magnet used should be neodymium with a delta connection. I would say that the objective is considered achieved as 850 watt of power can be produced by using 1 mm coil thickness from the simulation. And it also can produce 24 volt of voltage that is enough to charge a battery. With that, thank you for lending your ears.